Hi there, welcome back to the second video that we're recording on latent variable modelling using R. I'm Robert Cleary and I'm here with
Tassos Pagassilis.
Yeah, and if you watched the first video, we just talked a little bit about latent variable modelling and how it differs from other types of factor analysis.
Exploratory factor analysis.
We've opened R, we've put some data in it, we've called and loaded the packages we need, which is lavaan and semPlot. We've created our model, which is this code here, and we've created an object which has actually now done the CFA analysis for us, which is called fit. So what we're going to do now in this video is talk through the results of our CFA and think about the outputs of semPlot, a kind of nice visual image of the model that you can get. So first up, let's look at the results, and I'm just going to copy and paste a bit of code. So the way lavaan works is you have to create an object, usually called fit, which does the analysis for you, and then you need to call that object and call a sort of component or a bit of that object. So in this case, we're going to use the summary function, and we're going to say, give us the summary results of this object called fit that we've already created. And we want standardized results.
So if we make a small stop here, I think it's good to discuss the issue of standardized versus unstandardized results.
Good point, let's do it.
Generally speaking, we want standardized results, and we look at standardized results in order to be able to compare across different models. So because usually you start from very similar models and then you change a couple of parameters, and then you want to see what the effect on the model is, especially if you're adding in new variables or taking out variables or changing the value of a path or a parameter. So that's why we call for standardized results. Generally speaking, however, when we are writing text, so when we are reporting on our results, we want to use the unstandardized results.
Maybe just say what the difference is between standardized and unstandardized, because not everyone will know.
Okay. So the difference between standardized results and unstandardized results is that the standardized results, the parameters have been standardized to belong to a distribution that goes from 0 to 1, and it doesn't take any other values, while the unstandardized results, they are given in the value of the items. So depending on the scale of the items that we use, in our case it's 1 to 10, in another case it might be 1 to 7, the unstandardized results will be given in values of that item or of that latent variable.
So they're unstandardized because they depend on the scale that you measured them in, so they're not standardized to other models.
Exactly.
Got ya. Okay, so the summary function doesn't give you the standardized results unless you tell it to, which is to say standardized true. And we're also going to ask for fit measures.
We always want to know how well our model fits our data, so fit measures are definitely something we want to check every single time.
And that's like we were talking about in our last video, that the latent variable models are the results tell you how well your hypothesized relationships play out in the data. That's what fit means, is how well does the data fit to what you thought you were going to find. So if we press enter to this, let's see if we get an error message. We didn't, but we did get loads of results. So let's go up to the top.
So let's go up to the top and start trying to see the results. So the file starts very normally. You get the optimization method. You get the number of the free parameters, the number of observations. That's our data size.
That's like your sample size.
Our sample size, yes. You find out the estimator, which is maximum likelihood. That estimator might change. There are other models someone might use, like weighted least squares and non-weighted least squares and things like that.
I think you can change them when you call the CFA here as a parameter.
I would imagine. there is some ability to change
There
that.
is, I'm sure of it.
Okay, and then we start with the model fit statistic. This essentially is nothing else than a chi-square statistic. It doesn't say it here, but underneath in the p-value it does say p-value chi-square. So our model fit statistic is a chi-square statistic essentially. There are no upper or lower limits in the chi-square. You always look at the chi-square statistic together with the degrees of freedom. The rule of thumb in the literature is that if you divide the chi-square value with the degrees of freedom, you should get around 2.5 or between 2.5 and 3. So the chi-square should be 3 times the degrees of freedom or 2.5 times the degrees of freedom. In our case, we see just by doing the maths that it's at 3 or a bit higher as such. And that's the reason why the p-value here has come out as significant. Again, ideally, you want this p-value to be non-significant, because that means that you don't reject the null hypothesis, you accept the null hypothesis, and the null hypothesis is always that your hypothesized relations do not differ from what your data have to tell you. As far as I've worked in my career in structural equation modeling, I've probably gotten an insignificant p-value in 1 or 2 cases as such. The data we use and the models we use tend to not produce insignificant models, they tend to produce significant models, which always means that the data don't necessarily fit our models so well. That is why a lot of people are then tempted to go out and play with the different models and play around with factor analysis.
And that might be like taking out a manifest.
Yeah, it
an indicator
could be
variable.
yeah.
Or
Yeah, it could be taking out a manifest or indicator variable. It could be adding in a manifest or indicator variable. It could be allowing manifest variables to covariate. So in CFA or in SEM, you don't want your items or your manifest or indicator variables to covariate, because if they covariate, it means that that covariation is not captured by the latent factor.
Yeah.
It means there is a third latent factor or some other reason that these variables covariate. So you want to make sure that they don't covariate. A lot of academics do tend to put covariations between the manifest variables, which might lead to a better model, but not necessarily a theoretically based model.
and then it becomes less parsimonious or a less
it
effective
becomes
way, because you're saying there's both this underlying latent variable that accounts for some, but then there's this other thing which we don't know about.
Exactly.
But we'll just say it's these two manifests have a variation, but we don't know why.
Yeah, exactly. It's always a good idea to test to take a look at the baseline model. So the baseline model is the model that you would have without any paths as such, or without any restriction in terms of parameters. And that's why it has a huge chi-square and more degrees of freedom than our model. So in our model we have constrained particular paths to behave in a particular way. Ideally, or almost every time, you should see your constrained model have less chi-square, so the value of the constrained model should be smaller than the value of the unconstrained model. If that is not the case, then something is going wrong with the model. In our case,
if that's the case, you can stop here.
Yeah, you can stop here and
start again.
Yeah, and start again. In our case, we have a smaller chi-square value, so we know our model is working. And now you start looking at some other fit indices. So here we have the comparative fit index and the Tucker-Lewis index. The Tucker-Lewis index sometimes is called the non-normed fit index, so the NNFI. These are both fit indices that show how well our data fit our hypothesized model. They run from 0 to 1. The closer they are to 1, the better it is. A common rule of thumb is to take a look at these indices and hopefully get them over 0.9. In our case, they're a bit lower, but they're not dramatically lower, so we can continue to evaluate our model as such.
Hey Tassos, I just thought of something. So when we're just talking about covariation and that sometimes researchers might add covariation between manifest variables, and you were suggesting that's maybe a clever, tricky thing to do. But what about covariation between latent variables? Because that's what we've got in this model. Is that better because you're actually hypothesizing a relationship?
Yeah, so in covariation between latent variables, you're hypothesizing a relationship, and for the most part, if you have two variables, if these variables are not linked directly by a predictive path, then they need to be linked by covariation. So if you are trying to run a SEM model, you can only have variables that covariate or variables that lead to other variables or predict other variables as such. If you try to run a CFA with two latent variables but no covariation, the software would also tell you that you're missing a covariance as such from your whole model. So you cannot technically run a model if there is no covariance between your latent when you're running a simple CFA as such.
Okay, so I interrupted you then. But
no, that's okay. Yeah. So we're moving along the fit indices. Now here you get a range of fit indices that unfortunately they don't really say a lot about your model. You get the log likelihood. This is our user model, and you get the log likelihood